Hello everyone, welcome back. This is a question from Pathfinder, check your understanding rotation chapter, and question number 21. This is an interesting practical application based question. Let's read it. To insert into or draw out a cylindrical rod tightly fitted in a circular hole, a usual practice is to apply a necessary axial force, push or pull, and simultaneously rotate the cylinder. So this generally happens. Let's say there is a cardboard and we are going to push the rod into it, tightly fitting. So we don't simply push it directly, automatically, intuitively we rotate and then push it, rotate and then push it, simultaneously rotation as well as pushing it. That's how we can do it much easier way. That's what he's talking about. Moreover, we do it in steps because by hands we cannot continuously rotate the rod because of the constraint. You rotate for some time and take out the hand, again hold it, rotate for some time and push it simultaneously. This is the mechanism happens. How does this technique work? Let in each step of duration delta t, the rod rotates at a constant angular velocity omega, omega constant meaning net torque 0, and advances axially by a constant linear velocity v. That means even linear velocity is v meaning acceleration of center of mass is 0, net force is 0. And in the process we are applying a constant axial push F there, axially we are applying F force. Find the torque tau that you need to apply so that this process can continue like this. So first part is, let's look at this diagram. It's very simple question. In the diagram only you can understand it. You consider the point which is on the top of the cylinder just touching the cardboard. It has got two components of velocity. One velocity is because of axial motion v and other velocity is because of rotation r omega. So it has got v and also r omega, both are horizontal only, perpendicular to each other. So that point has got net velocity not along axis, not along the circumference, circumferential tangential, but it is actually going to be at some angle there. This is going to be the blue color, net velocity root over v square plus r omega whole square. That is the velocity of this point of contact, which is just below the whole cardboard there on the cylinder. So this point has got a velocity in this direction. Now kinetic friction will oppose that velocity. So kinetic friction is neither along the axial direction nor along the tangential direction, it is at certain angle. And the value is mu into n anyway. So the force is mu into n, but the direction is at certain angle. Now you will have to resolve it into components. One component is along the axis, which is going to be Fk cos theta. So Fk is not there, Fk cos theta. So if you directly apply the force there, right, Fk will oppose it completely. When you rotate and apply the force, then what is opposing you is only Fk cos theta. So Fk opposing the axial push is reduced. That's why it becomes easier to push that way. So that's the idea of the strategy. That's a point of question A we can analyze. So when you are doing rotation and pushing, the force that you need to apply is not kinetic friction, it is less than kinetic friction to move it. That's why it is easy to do it. That's first part. Second part, let's look at it, and for that a bit of geometry. Look at this velocity triangle that we have here. So you have v axial, r omega circumferential. So we can write cos theta equals to adjacent side by hypotenuse and sin theta equal to opposite side by hypotenuse. Tan theta is sin theta by cos theta, which is r omega by v. That is geometry part. And also Fa is f cos theta and Fb is f tangential is f sin theta. And we have that Fa has to be opposed by axial push because velocity has to be constant. This f tangential will apply the torque there. F tangential into r will give the circumferential torque because net torque has to be there. So tau equal to Ft into r. Now if you divide these two equations, you will see Ft into r by Fa equal to nothing but r tan theta because sin theta by cos theta. And we can calculate tan theta from here, that is going to be r omega by v there. So if you simply adjust that, you will see the tau required would be f into r square omega by v, which is the answer. Very simple question only if you understand the diagram. So with that I'll conclude here. Thank you very much for joining. Until next time, goodbye.